Okay, probably I'm going to start. So before I start the talk, there was a talk yesterday about the difference between SPMV and double precision, single precision. Is this working? The other one? Okay, whatever. So, I mean, we know that usually in dense linear algebra, we expect 2x speed up between single and double precision. In sparse, I mean, in computation, we expect 2x. On the computation side, when you read the data, when it is like SPMV, it has IG, CSR format, it has the number of columns. So it has integer indices. Those integer indices will remain the same. It will not change between single and double, so they affect the memory bound operation. And for memory bound operation, we expect actually about 1.5 times speed up, or maybe 1.6. So between 1.5 to 1.6, that's what is we really expect to do SPMV between double and single precision. So I did ask my friend at NVIDIA to run the SPMV kernel and then for a bunch of matrices from the suite sparse. And we time those kernel, and then I'm putting the speed up here between the single over the double. So 2 is twice faster, 1.8, 1.6. This is how much it is faster. Those matrices range on size from 4,000 to about 21 million. And this is the size, about the number of N and Z on those matrices. And if we look to those matrices, most of them have a speed up above 1.5. The GEO mean is about 1.54x speed up. So we are really actually reaching the peak between single and double precision, even on SPMV. So, and this is run by CUDA 10.2. And there is a lot of improvement that happen at CUDA 10.1, 10.2, and more is coming, specifically on the SPMV kernel. So, I mean, just this is talking about the difference. Okay, so I'm gonna talk about Tensor Core Accelerated Iterative Refinement Solver. And so using most likely mixed precision and their impact on scientific computing, or specifically for HPC or future design of the hardware. So if we take a look today on what kind of peak performance we can get from the current existing hardware. So if we run 60 on a Volta GV100 and GPU, if we run the 64-bit, I mean, this is a theoretical peak, 64-bit floating point is about 7.8 teraflop. The 32-bit should be twice, so 15.7. The 16-bit floating point FMA, it should be twice the single, so 30. Maybe it should be 31, I made a mistake, but whatever. And well, I mean, there is something new that has been introduced at NVIDIA, and it was driven mostly by the deep learning and the machine learning computation. For them, when they tried this FP16, the result was okay. So it was driven by this technique to introduce FP16. So they introduced FP16 gem-like kernel, which they call it Tensor Core. And actually, it is not FP16. It's an FP16 plus an FP32. It's better than FP16 and a little bit less than full FP32. So they call it Tensor Core, and this hardware is able to provide today 1.5 teraflop peak performance. It's about like 6 to 8 times the single precision performance with a result which is between FP16 and FP32. So this is amazing. It's a tremendous performance difference between 32-bit and 64-bit. So can we take advantage of this in HPC the same way that deep learning people take advantage of it? And before I start, let me give you a quick overview about what we have today. We have the Summit supercomputing system, which is #1 supercomputer. And if we look, it has a peak performance of 200 petaflop, double precision. Summit has about 4,600 nodes. Each node has 2 IBM core and 6 NVIDIA V100 GPU. Now, if we look here, look what's going on. Look to this number here. It's a 3.3 exaflop. Amazing. 3.3 exaflop if you run on the Tensor Core. From 200 petaflop to 3.3 exaflop, we can get it if we utilize correctly the Tensor Core. Now, deep learning, use it right away, and they show many applications that run above 1 exaflop using the deep learning. So can we do this for HPC? Can we try to get there on HPC? And this is about what this talk is about. Note that if you look to the CPU provides 2.3% of the system performance, and 97.7% of the performance are from the GPU. So who cares about CPU? I'm joking, I'm not, don't take it on me, but just trying to say that today we have really to focus on getting performance from the GPU, so you focus on 98% of your performance, how to get there. If we get this, we are really at the peak of the machine, and very good stated. So most of the real-life applications, they need to solve either eigenvalue problem or linear solver. I'm going to talk about linear solver. What is linear solver? Linear solver is solving this famous equation, AX equal B. How to solve this? Well, there is a nice way which say we have to transform A into a nice form. So we take A and we split it over lower and upper part. So A equal LU. We transform A to a nice form. Why we say nice form? Because L and U are very nice. That's the way you solve the system if you have lower and upper triangular. It's very easy to solve. We know how to solve this very easy and very fast. So the question is how to transform A to LU. That's what we call an LU factorization. How it works? That's how an LU factorization works. It computes an LU on this orange portion, the panel we call it. And then it applies this LU to the purple side here. And then this means this portion, the white portion here, has been factorized. Now we forget about it, we move to the next side. So you factorize this, you apply it, you update your Schur complement, and updating Schur complement is a GEM operation. GEM is matrix multiplication. And then once you are done, you move to the green portion here, and this is the green portion, and you factorize it, and you move on, and you move on, and you move on. So when you look to the algorithm, how it works, you're going to realize it is mostly dominated by GEMs. This algorithm costs 2n³ / operation. Those 2n³ / operation are in the GEMs. 80% of the time to 90% of the time for large size are spent in the GEMs. And we just saw that the GEMs can be accelerated by Tensor Core from 7.8 or 7 teraflop to about 100 teraflop. So can we use this, the Tensor Core, to accelerate the LU and still get the FP64 accuracy? So let's start by GEM. Before we start coding and developing, let's see where is the GEM. Can we get something there, or what is our upper bound? So if we take a GEM on FP64, it reaches about 6.4 teraflop, which is the peak expected. If we do single precision GEM, it is about 14 teraflop, like twice faster. If we do pure FMA, FP16, it's about 27 teraflop. But if you do Tensor Core, which are better than the blue line here, why better? Because Tensor Core do accumulation in 32, and they do multiplication on full precision. So it's somewhere between FP16 and FP32 toward FP32 in terms of accuracy. So if we do FP16 Tensor Core, we are 12x faster than the double precision. It's amazing. It's great. If we can use this GEM in the LU, we can expect to get 12x. Well, not. It's not 12x, because if you remember, the LU has specific shape for the GEM. It has this shape for the GEM. It's a rank K update. The size of the GEM is like this. It is not a square GEM. But however, this GEM still performs today at 36 teraflop. And we believe that in the future, it might be optimized to reach around 50 teraflop. So today, we are around 37 teraflop on the Tensor Core using this kind of rank K update, and for small k. If k get bigger, it gets closer to the peak. So we choose 256 and 512k, that is for algorithmic reason. So now what we're going to expect, if you implement your LU using the FP16 Tensor Core, you are going to, and since the GEM is about 80 to 90% of the time, if we get here 7x speed up over a GEM, we can expect that LU will be somewhere between 4 to 5x speed up over the FP64 LU. So we did LU, and here the orange, I'm going to follow those colors over all my slide. The orange is double precision, the purple is FP32, and the cyan is FP16 Tensor Core. I don't care about FP16 only, FMA, because it doesn't exist anymore for me. Since Tensor Core are there, are better accurate, why use FMA, FP16? So if we implement this LU using those 3 precision, we get 4x speed up using the tensor core. So now anyone who has an application that you solve AX equal B using the LU, he can expect to get 4x speed up if he switched to FP16 tensor core. Great. It's really great. However, I mean, it has some approximation because this guy ran FP16 tensor core, so the solution is not really FP64 solution. How we fix it? There is something called iterative refinement. And iterative refinement means we fix the solution. So you do your LU on lower precision, and then you iterate, and you fix the solution. So how you fix it? It is called classical, like it's a loop here where you compute the residual, and you compute a correction to the solution, and you iterate again, new residual, a correction to the solution, and you keep doing it until you get the solution. It is well known as the classical iterative refinement. That's the way you solve this equation. You have the LU of A, you solve it this way. And recently, Nick Hayam and Aaron Carson, they did introduce to use GEMRES, precondition GEMRES, to solve this equation, because it's more stable and give you better solution. So if you use this one or this one, both of them, you're gonna get a solution here, you're gonna fix it, and when you finish this loop, your solution is going to be down to the FP64 accuracy, even though your LU was FP32 or FP16 done. Note here the flops. Now, all the flops are done on lower precision. So in terms of time to solution, we're going to expect to keep this 4x speed up or 3.5x speed up if we do just 2 or 3 iterations. We did some work here, and we show that we can get around 4x speed up using this technique. Lower precision FP16, LU, and iterative refinement using either classical iterative refinement or GEMRES, or also using the whole GEMRES to solve AX equal B as well. So these are like 3 refinement techniques that we can use to solve the problem and converge to the FP64. I think I'm going very slow. So the solver provides 4 to 5x speed up. It has shown very interest on many applications. Even DOE ECP Exascale project is interested on developing stuff like this. So Magma has this solver released since 2.5. CUDA Solver 10.2, which got released in November 2019, has the solver as well. We have both real and complex case, as well as multiple right-hand side. So if somebody is interested to try this, he can download it and then try it right now. And more functionality, algorithmic feature are coming soon. How about performance? So I have been talking about how it works, but how about performance? So this is a small chart about what you can expect as performance. Again, orange is double precision. Purple is our solver running the LU in single precision and then iterating to get the double precision accuracy. And cyan is the TCAR solver running the FP16 LU, the mixed precision LU, and iterating the solution, refining the solution to get the FP64 accuracy. So at the end here, the user gives you a double precision matrix and get a double precision solution. You can run any of those, and you can expect what you can get. Teraflop here is 2n³ divided by time, so twice higher is twice faster. Conversion, whatever happening underneath is included in the timing. So this timing, you give a matrix A, you give a matrix B, and you tell the solver, give me a solution X. And the solver gives you a solution X down to the FP64 accuracy, using any of those 3 methods if you want. And if you use the tensor core, you're going to get 4x speed up with the same solution as FP64. So that's the whole bottom line lesson from this work from the TCAR solver. And it works for many matrices. For sure, for some hard matrices, it may not work, but there is some technique to fix it as well. Now, if you are the condition number of the matrix here is around 10 to power 5, between 10 to power 4 to 10 to power 5. This line here shows that on this axis here shows the condition number of those matrices chosen in this experimental case. So, if you are wondering also about the number of iterations that it took to converge, this is the number of iterations. It took, if you use the FP32 as a lower precision we call it, so if your LU is on FP32, you need about 2 iterations to converge for this type of matrices. And if your LU is mixed precision FP16, it needs about 3 iterations to converge. So we just do FP16 LU, 3 iterations of refinement, and you get a solution down to the FP64 accuracy with a 4x speed up. I mean, isn't tremendous, amazing speed up? Now, how about multiple right-hand side? We run the same code, but instead of having one right-hand side to be solved, we run multiple right-hand side. So we run 32 right-hand side. The multiple right-hand side code is not fully optimized yet, so we still have some gain to get it better. But even with this, we don't lose much. We lose just like 5 to 10% in terms of performance. In terms of number of iteration, it's roughly the same. Sometimes it's plus 1 or 2 more iteration. For this case, it's the same number of iteration to converge. So with the dashed line here, you can get 32 right-hand side solution for the same problem with just 5 to 10% overhead. So we're still reaching around 4x speed up. And this is also great. How about harder problem, different problem? We run a harder problem here. It took, you see, 13, 14 iteration, 15 iteration to converge the tensor core version, and we are still getting 3.5x speed up. So we're still happy, and it's still working, even with 15 iteration. I show you here the double precision. I'm going to skip this. I'm going to go quickly over the complex. So the code works for complex. On complex, even it is better because it has more intensity. So it can reach 5x speed up. Now, how about other problem, real life problem, sparse problem? So we get some sparse problem, and from the Florida collection. So this is what is called FEMLAB. It's a Navier-Stokes equation, NS3DA. That's the size of the matrix. This is the condition number of the matrix, 10 to the power 3. And we run the double precision, and we show the final residual of the double precision here. And we run our solver, the TCAR solver, using the FP32 and converging to the FP64, and the FP16 tensor core converging to the FP64 using the 3 type of refinement. ER, classical ER, geometrized is geometrized on AX equal B, and ER geometrized is iterative refinement with geometrized internal. It's just, I mean, all of them are iterative refinement. The TCAR solver was iterative refinement, and you can see it does 4 iteration, it converge, it's great, it's amazing, and the final solution of the same accuracy as double precision. So you can expect 3 to 4x speed up on this type of matrices. Now, does it work for all those type of matrices? No. Here we run it on a harder matrix. It has a condition number 10 to the power 11, and it do not easily converge. It converges within about 30 iteration. The generalized version, the ER generalized version converge about 38 iteration. The classical ER, the existing standard ER, did not converge at all. Well, it did, I think, if 50 iteration, and we stop at max iteration equal 50. So at 50 iteration, it was not converging. Now, for this type of matrices, there is some remedy we called, or some algorithmic advancement, some technology. We can do some magic sauce if you want. So there is a scaling, there is other. I'm not going to talk about the other, but the scaling is one of them. So we do diagonal scaling. We scale the matrix, and then we run it. And now we converge around 8 to 9 iterations. So it's amazing. We even, with this harder matrix, we can converge at 8 iterations with doing some techniques. So it's not only FP16, there is some treatment that has to happen, but it does not affect that much the performance. So and overall, we run a bunch of matrices from the sweet Florida collection, and the speed up for the tensor core is about between 2.7 to 4. So we are getting a solution between 2.7 to 4 times faster, just by using the tensor core accelerated solver. Does it also work on another real life problem? Yes. There is a collaboration with people from Oak Ridge. We run the plasma fusion to steam and stability. And we switch the solver from a basic FP64 solver to our solver, and it ran, and it gives us 3.5 times faster solution. So even with those simulation, we can get 3.5 times speed up just by switching the solver. The user doesn't have to do anything. He just switch one line of his code, use this solver, and get the benefit right away from the mixed precision. Quickly going on, because I don't want to hold you from the lunch, I show that it is faster time to solution. How about energy saving? So does it help? Well, we plot the energy consumption of the CPU plus the GPU, even though our code is GPU only, so it doesn't use the CPU, but the CPU is idle. We take the power of the CPU, we put the power of the GPU, and we run. So again, the orange curve is FP64 DGESV. The purple is LU done on FP32, and we converge it to FP64. And the cyan is run on FP16, we converge to FP64. And you can see here, this get 5.3 teraflop, the other one 10 teraflop, and here is about 22 teraflops, so about 4x speed up, great. And so 4x speed up, it finished early, very early. And so you get about 94 gigaflop per watt versus 21 gigaflop per watt. So it's about 4x to 5x benefit in terms of energy because we are faster. So we can even decrease the energy consumption if we do this. So it's really great, amazing. I'm gonna say it's worked for many cases, but we still find some cases that doesn't work, and we're still working on some other technique to fix it. It has very good energy efficiency. So we want to go a little bit more and try this on really larger scale. So what we did is something we call HPL AI. It's a mixed precision HPL benchmark. So it is exactly the HPL benchmark, it's the existing LeanPack HPL benchmark, where we modify it to use the Tensor core. So we don't do a full FP64 HPL benchmark. We do a HPL benchmark, and then we use the Tensor core inside this LU. Now the solution is not great, so we do refinement to the solution. We refine the solution to get the FP64 accuracy on the HPL benchmark. So what we did in November is we take this benchmark and we run it on a matrix of size 10 million on the whole system of Summit. Actually, not the whole Summit. We did 4,500 node. So around 27,000 GPU. And we run this benchmark. So to give you an idea about the benchmark is for ranking the supercomputer machine on the top 500. Summit provided 148 teraflop for double precision HPL benchmark, and it was ranked #1 on the top 500. Now we run this benchmark using the mixed precision, and we get about 550 petaflop. So 3.7 times faster than the double precision. And both of the solutions are down to the FP64 accuracy. So we get the same solution as the basic HPL, 550 petaflop. We score 550 petaflop, like half exaflop, 4 times faster, about 3.7 times faster than the double precision. So we are happy from this. Even it worked on distributed, it worked on very large scale matrices. And there's still a lot of work to be done. There is a lot of research happening everywhere. And this is great for us. So thank you for your attention. And I am open for any question.